This is section 12.1 homework. And number 1 is asking us, write the given quadratic function in standard form. Well, we really didn't go over that much of standard form. The standard form is going to look like this. Y equals ax squared plus bx plus c. And just keep in mind that the a, this b, and the c are very important here. Okay, when you're identifying those coefficients. Those are called coefficients. And why is this thing a quadratic? Well, it is a quadratic function because the degree of this function is a 2. The exponent is 2. Please make note, if we're dealing with linear, linear is y equals mx plus b, and you notice that the exponent is 1. So linear functions have a degree equal to 1. Quadratic functions have a degree equal to 2. And the shapes are different. Linear, straight lines. The quadratics, when you graph them, they are parabolas, either opening up or they open down. All right, continuing. This equation here, you'll notice we have 2x squared equals x plus 4. They want it in standard form, so we've got to get one side pretty much equal to 0. So you've got two options. We can subtract x and subtract 4 on each side. And this will give us 2x squared minus x minus 4 is equal to 0. Because 0. There is nothing left on this side. Nothing left at all. These create zeros. Now, if you're going to write this as a function, we don't really want it set equal to 0, so we can just write it as 2x squared minus x minus 4 is equal to y. Or you could do f of x, g of x, whatever you want to name it using function notation. Now, the other option. There is definitely another option. Let me write that over here. 2x squared equals x plus 4. If I decide, I could take this 2x squared and move it over onto the right, so I can subtract. Now, just curious, on this left side, what's left here? 0 now, right? So I have 0 is equal to negative 2x squared plus x plus 4. And then you can write it in function notation, or y equals, whatever you want to do. How about I just call it f of x just for the example. Now there is a difference between both of these when you graph them. Let's take a quick peek at what that would look like. Alright, let's put this in the middle here. We'll head up to y equals, and let's do the positive leading coefficient of 2. So I have y equals 2x squared, and then minus x and minus 4. If I graph this, and I'm graphing it on a standard window here. And how do you quickly access a standard window? You just go up to zoom, and then number 6 is a standard window, and standard meaning 10 by 10. Okay, so you can see this this first function being graphed there. And notice, look right here. See that 2? That is a positive. That means the parabola is going to open up. Now let's take a look. Now I'm going to graph this one now. And they are different. They are definitely different, but they have something completely, there's a relationship between them. All right, head over to y equals, come down to y sub 2, and I'm going to do negative 2x squared plus x and plus 4 and graph. How do you think they're related? They're kind of opposites. They're actually reflections of one another, aren't they? Do you see that? Do they have the same, this is probably something you had an issue with last night, but do they have the same x-intercepts?
Yeah.
They actually do.
Yeah.
Absolutely they do. Just let's take a moment, head over to this screen, and if I pull this out and we can kind of examine this a little bit larger. There we go. That is an x-intercept, and that is an x-intercept. Now I can't come out and tell you what exactly those x-intercepts are because they don't land on a nice lattice point, meaning I can't tell what this is right here. Maybe it's like 1.8, something like that. But the calculator has a way to do that, and we'll be going over that shortly. But they have the same x-intercepts. One of them is heading down, and one of them is heading up. How can you tell that a quadratic is going to be heading up? You can say it out loud. No. Up. Pointing up with arrows up. Yeah, it's going to be y is equal to, and I believe this one started with 2x squared, correct? Let me double page this so I want to see exactly. It was 2x squared minus x minus 4. Minus x minus 4. And you'll notice this is positive. So that tells me that it's going to be heading up. And the other one, this red one here, it's heading downward. So it's y is equal to negative 2x squared plus x plus 4. Pretty easy to tell the direction of opening, correct? Let's head back. Now, in this problem, they are also asking for whether they have an absolute maximum or absolute minimum. Didn't it depend on which side you got all the variables? Totally. Yeah. If I head over to the graph, let's look at the blue one for a moment. This blue parabola. Do you think the blue parabola has an absolute maximum or minimum? Minimum, right? It has a minimum. Yeah. It has a low spot. And let's highlight that low spot right there. That's a minimum. And the red one has a absolute maximum. So we call that right there a maximum. And there is a technical reason they call it absolute maximum. When you get into integrated math 3, there are things called local maxes and mins. Because sometimes a curve will have more than one maximum in certain areas. Okay? Do you agree that a quadratic, in this case, let's talk about just the red one for a moment. Do you agree it has one maximum and that is it? Yeah, that's why they call it an absolute maximum. There's only one of them. Only one. All right. Number 2. Rewrite that in standard form. So number 2, let's take a look at this one. I've got to take this x and distribute it. So we'll do f of x is equal to x times x is x squared. Perfect. X times 3 is plus 3x. And if you want, you could write plus 0. That's fine. It's always a good idea to indicate what a, b, and c are, even though they're not asking us to. The a is equal to 1. The b is equal to 3. And the c is equal to 0. All right, let's take a look at this next one over here. I'm going to take, can I add the 5 yet? I cannot add that 5. Let's make this a little bit larger for you guys. How's that? I cannot add that 5 just yet because that actually goes against our order of operations. 10 does. So, erase that. What should I do first? Yeah, I've got to distribute this 3x. So we've got this f of x is equal to, now help me out. What's 3x times x? 3x squared. Very good. And then 3x times negative 8 is minus 24x, and then plus 5. Tack that 5 on the end. Is that in standard form? Yes, it is. So we've got A is equal to 3. B is equal to negative 24. And C is equal to 5. Okay, quick question. Is this function going to be opening up or down? Which one? Absolutely up. Reason being, that 3 is positive. Going to be opening up. Number 4, it says the citizens of Harrington County are wild about their dogs. They have an existing dog park for dogs to play, but have decided to build another one so that the park will be for small dogs, and then the other will be for the large dogs. The plan is to build rectangular fencing in the area that will be adjacent to the existing dog park. Okay, so we've got this happening. This is our existing, I guess, old dog park. We're going to build a new one. The new one is going to be right here. How many sides of fencing do we really need to build this thing? 3, yeah. We've got to get some fencing for this side, and this side. There's already existing fencing right here. We don't have to even take that into consideration at all. So, some important information up here. It states that the county has enough money in the budget to buy 1,000 feet of fencing. Okay, fine. Determine the length of the new dog park in terms of W. This was very difficult for me when I was your age. Understanding even what they meant. They're saying, write L in terms of W. And what that means is this. You're going to write an equation, L equals, and inside here somewhere there's going to be a W. That's what they mean. So what do you think? The length, what do you think here? This. Well, once again, they're asking for L in terms of W. Well, let's just put this, let's try to kind of wrap our heads around what's happening here. How much fencing are we going to use? 1,000. 1,000 feet. Okay, so we have 1,000 feet of fencing. Is that going to equal something? That's going to equal what? 2 times the width. 2 times the width, because we have 2 of them. But plus, should it be 2L or 1L? 1L, yeah. Let me make a cursive L so it doesn't look like a 1. Now, if you wanted to get the L by itself, just so that we meet their request that L is in terms of W, what could you do to get this L right here by itself? Subtract 2W. And here's what you got. You've got L is equal to 1,000. Go ahead. Minus 2W. And now L is written in terms of W. Okay? Makes sense? Part B. Part B says, write a function for the area of the new dog park, A of W. So they're giving it a function name right there, A of W. In terms of W. And then write the function in a standard quadratic form. Does this function have an absolute minimum or an absolute maximum? And explain your answer. Okay, so we need A of W equals something. And over here, you know there's going to be a W. So take a moment. So we want this area function, right? Do you agree that we are finding the area of what seems to be, I know it looks like a square, but we can only assume it's a rectangle for now. Let's just assume it's a rectangle. How do you find the area of a rectangle, folks? Length times width. And in our case, we do have a length and a width. The length and the width are going to be right here. Here's your L, here's your W. So I can come down here and say L times W. But I would like to have just W over here. How can I have just W over here? I don't want the L there anymore, because I want it just in terms of W. What do you think? Preston?
Since you know what L is equal to up there, you just substitute that in.
Yes, folks, this is already equal to L, so 1,000 minus 2W can take the spot of that L. Do you see it now? All right, here's what we've got. A of W is equal to 1,000 minus 2W multiplied by W. Yes. Hey, they're requesting something important here, though. What are they requesting? That it's in standard form. Okay, right here. Has to be in standard form. So let's just go through and distribute. All right. Let's bring my work up here. A of W is equal to W times 1,000 is 1,000 W. W times negative 2W is minus 2W squared. Now, technically, this is not in standard form yet, right? So we have A of W is equal to, I'm just going to take this one and just write it first. If I do write it first, should it be a negative or a positive?
Negative.
Negative, very good. So negative 2W squared plus 1,000 W. Okay? There's your quadratic. Very important. All right? Now, determine the x-intercepts of the function and explain what this means in terms of the problem situation. I can't emphasize this enough. All right? Question?
They also ask for the absolute minimum maximum.
Oh, on this one, yes, absolute minimum or a maximum. Okay, perfect, thank you. This one here, do you agree, if this is a negative, tell me about the shape of this thing. It's going to open down, right? And if it opens down, draw yourself a little picture. We know it's going to open down, therefore, you can kind of see that right there, that's going to indicate it's going to have a
Absolute maximum.
absolute maximum, yes. Yes. Good. Part C, determine the x-intercepts. Now, I can do this algebraically, but they haven't taught you that algebraically. What we have to work with is our calculators. In IM1, I'm not sure if we covered this, but anytime you want to find an x-intercept, I know I'm kind of stretching here, but do you remember how to find an x-intercept at all? Or is that really foreign to you? X-intercepts. To find an x-intercept, you plug in what for y? Zero. You plug in 0 for y. And the only problem is, I don't see a y up here, do you? So it's not like you just plug in 0 for y. You plug in 0 for the dependent variable, for the output. I could rewrite that equation like this. Y is equal to negative 2W squared plus 1,000 W. And I don't even have to write the W if I don't want. I can come over, grab an eraser, take the W's out, and I could make those X's if I want. If that makes you feel a little bit more comfortable, that's fine. Now, how do you find an x-intercept? Well, what we do is we take this y and we let it equal 0. So 0 is equal to negative 2x squared plus 1,000x. And then you have to solve that. But folks, you do not know how to do that just yet. We don't. Okay, you have to do a lot of factoring right here. Then you have to apply the zero product property. Those are things that we have not taught you yet. So we have to go strictly to the calculator. Head over your calculator. Let's turn this on. And head up to y equals, and I'm going to clear everything out. and let's just focus on the function at hand. So this function I'm going to be dealing with is this one right here. That's what I'm going to enter in. All right, so I have negative 2x squared, and then plus 1,000 x. You already know what the problem I'm going to run into is, correct? What is it? The window. I have no idea what the window is. So here we go. I'm in a graph, and I'm on a standard graph. You might see maybe something here, but that's it. Yeah, I see a blue line go up the top. So let's think about some strategies on how to see this whole thing. Okay, how to see the entire parabola. Well, let's head up to window. Let's talk about what the x means, and the x is our w, right? It's the width. Let's pick some widths here. Go ahead. Shout out some widths that you would like me to plug in. Go ahead, Alex.
I got the X minimum be 0, because it doesn't need to.
Sure. X min 0. That makes logical sense, right? Let's do this so that everyone can see it if you're watching the video. There. There we go. That's 0. How about X max? This would be the maximum width of this new dog park, this new portion of the dog park. Okay? Yes? All right. Ideas. Preston.
500.
You want to go 500?
Yeah.
Okay. Is it okay that I go 800?
Sure.
I have a reason for that. I want to have a larger window to look at this quadratic. Yes, Lucas.
Maybe go farther than 0, like negatives.
Okay, I could do that also. I can take this minimum right here, right? And how about I make it negative?
Like 200.
Negative 200 if you want. Okay, fine. Fine.
1,000 range.
And you guys know that I can always adjust these again. It really doesn't matter. All right, so go ahead.
For the Y max,
You want me to go to Y max? Go ahead.
90,000.
90,000. Okay. 90,000, yes?
I got 150,000.
150,000? All right. So how about, I hear a bunch of values coming out at me. I'm going to go higher than all of those. I'm going to go 200,000 just to see what happens. Graph. I see it come up and come back down. Is that a decent enough window to start exploring? Yeah, absolutely. All right, now what do we need to do? We need to, on part D here, it asks us, oh, sorry, we're still on C. We're asked to find the x-intercepts. All right, well, I'm going to take this picture. Let's drag it over for a moment. Talk about what we're trying to find here. Do you guys agree that I'm trying to find this highlighted point and this highlighted point? Where the graph intercepts or cuts through the x-axis, right? Okay, there's a way to do this. So watch carefully. This is kind of brand new. These are the steps that you need to go through on your calculator. All right, here are the buttons. We're going to do the second, calculate, and you will notice right there we have some options. And our options value, 0, minimum, max, intercept, dy over dx, and then some integral stuff. We're going to focus on 0. A 0 is really an x-intercept. Okay, keep that in mind. A 0 is an x-intercept. So I'm going to choose number 2. Now notice where my cursor is. My cursor is right here. I want to get it over near the point that I'm seeking. Now, how many points or x-intercepts do I have? I have 2 of them, so I have to kind of do this twice. So I'm going to go ahead and I'm going to scroll over. I'm going to hit the right arrow. Let's get over near the one I'm seeking. I don't have to be right near it, but look what it's asking for. It's asking for a left bound. Do you agree that my blinking cursor is to the left of the point that I'm seeking. Is it to the left? It's still on the graph, right? It's to the left. So I'm going to hit enter. Notice what it did right there. It actually drew a vertical line, and it has a little arrow. Okay, so we're going to find to the right of this line, and look what it's asking for. It's asking for a right bound now. So I need to keep scrolling, and I need to go to the right of the point that I'm seeking. Now, I don't even see my cursor anymore. Maybe I could have changed my window, but do you think that the cursor, isn't the cursor underneath here? You just can't see it. Am I to the right of the point I'm seeking? Well, most certainly I am. Hit enter again. All right. It's asking us to guess. You don't have to worry about anything there. You're going to select it again. And look, did it give us the x-intercept? Most certainly did. And that x-intercept should be in ordered pair form. Ordered pair form. Watch. Okay, so that x-intercept is 500, comma, 0. And you've got to understand that when y equals 0, x is equal to 500. All right? So let me record that. Okay, the other x-intercept is right here, and it is absolutely 0, comma, 0. Now, on any kind of assessment we give you, I'm going to tell you right now that you are going to have to explain what these points, what these x-intercepts mean in terms of this problem situation. Okay, you're going to have to explain what this means. Let's just point at this 500, comma, 0 for a moment. Now, I know that they are x, comma, y, but in our case, in this problem, what variables are they? Yes, Lucas?
The width and length.
The width, no. The width and the?
Area.
The width and the area. Yeah. These points are in the form w, comma, a of w. And you can kind of see what they're talking about here. Yes, Spell.
Was it the width is 500 or 0, but the area will be 0?
Yes. Yes. Go ahead.
And for the one that's 500, the length, you go back to the original problem. The fencing is thousands, and there's two widths, so it'd be 500 plus 500, so that'd be thousands. There'd be no more fencing to close the figure.
Absolutely, yes. If this was 500 and this was 500, you've used up all your fencing and you couldn't even close the gap here, then that means that the area that these dogs would run around in would be 0. There would be no area to run around in. Okay? Now, I don't think that we would like to enclose our dogs like that with 500 as our width, correct? So we need to kind of look down at this example here, part D, and it says, what should the dimensions of the dog park be to maximize the area? What is the maximum area of the park? You go back to your calculator for a moment, right, and have this discussion. Where would be the maximum area? Where would that be? Even on the parabola, where are you looking at? Up top? Right? Here. Bring this back down so we can draw on it. Now this is a very, this is something different. As I scroll up, as I am going up this parabola, any kind of parabola or any kind of graph like this is made up of points. And every point on this represents the width, comma, area. And so you want to ask yourself, where is area at its max? So where would the area be at its max? Yes?
250. Why would we talk about it first when we try to set it up?
Yeah, I believe so. And here's what it would look like if we travel to the right along the x-axis, and then we travel up. We're going to be looking for that vertex. That's what we want to find, the maximum. And we did that yesterday on the calculator. Let's try it again. Take the calculator out. All right, so second trace. Make sure I have this out so you can see it. I'm going to find the maximum, number 4. I'm looking for a left bound. Am I in the right spot? Can I just hit enter right now? I need to be to the left of the point I'm looking for. I believe I surrounded myself there, and there it is. Now, because the calculator kind of uses a calculus method right now to find out where that maximum is, and the calculator has just a finite number of pixels, you'll notice it's indicating that we have 249.99999. Really, that number is 250. Good. So I'm not even going to say that x is equal to 250. I'm going to say, with respect to this problem, that the width is equal to 250 feet. And when the width is equal to 250 feet of fencing, the area, A of W, would equal 125,000. Correct me here, it shouldn't just be feet, it should be square feet. This is the largest amount of area that these dogs have to run around in, and you need to take this into consideration before you build it, right? So if the width is 250, the dogs have a lot of room to run around. This is the maximizing area problem. Now, we've already set our window, but what if you had no idea how to set your window? Let's think about this for a moment. If you've got this, you're going to have dogs running around this park, right? This one is already taken. We don't have to worry about that side. But how much fencing do we have? We have 1,000. Here's your W, here's your W, here's your L. And your function was A of W is equal to, I believe it was negative 2x squared, and then plus 1,000x. All right, and I should make sure that I'm not going to write x's in there. I'm going to put my W's in. Let's think logically about this. Should I set the W just equal to like 50? Probably not. How much fencing do I have? 1,000. Okay, so logic tells me that I can go up to probably 1,000, but that's not, I mean, I have 2 widths, so I have to spread out this fencing evenly somehow. Yes?
If we figured out what W was previously, couldn't you just plug that number back in to find L?
You totally could. Yes, you could. Yes. So what I'm just coming up here is this window, and I would say, for our window, I don't have to set this X max to 800. I could do 600 and graph, and it would still come out pretty decently. All right. What are some ways to find the Y max? I'm not sure if you think about this, but what if this were, let's just say, you started jotting down a drawing. You said, that's 600. Well, that would have to be 600. Is that possible? That's not even possible, is it? Have we run out of fence? Yeah, that's 1,200 feet of fence. So you've got to go backwards, and you've got to start erasing. All right? Let's go with 400, 400, right? Let's just throw numbers down. What would the other part have to be? What would this have to be now? What? 200. let's just find the area for this example, just for the heck of it. See what happens. What's 400 times 200? Help me out there. What is it? 80,000. 80,000. So that actually, just by coming up with a simple example, will give you a possible window to begin with for area. You would open up your calculator, head up to window, and I know I have 200,000 there, but I'm just going to select 80,000. And just watch what happens. Goes up, and you're like, oh no, I didn't get it all. So I might want to,
Raise it.
yeah, I want to increase. Okay, I want to increase that value again. So I'm going to head over to window, and I can just increase this. And I can go with, well, we did maybe 160,000. Oops, that's 16,000, so I'm really not going to see it. But, oh, by the way, if you ever want to pause your graph because you hit something by accident, hit the on button and it will pause your graph. Then you can start using your calculator again, okay? This calculator is a little slow on here, but now graph. Okay, I'm not sure if you're understanding what I'm trying to get at here, but can you use some common sense and plug some numbers in? Draw something to come up with a window? I think you can, yeah. F, use the graph to determine the dimensions of the park if the park was restricted to 105,000 square feet. If it was restricted to that. How in the world would you find that? This was a part of your homework last night. You must have gotten to this problem and been like, what do they want us to do? Lucas, question? Go ahead.
Well, since you have, since you graphed it, I actually ended up plotting that area. So if you have the area of 105,000 feet, if you find, let's say you plotted 150 in the graph, got that value. Well, I didn't do this algebraically, but
Gotcha.
go on the other side of the graph too, and then 350 is the same, because the max is,
What was our maximum area anyway? From the first page, guys. What was our maximum area?
25,000. 120,000.
125,000. But let's say we're going to restrict. We're like, hey, that's too much. That's too much room for those dogs to run around in. And we're only going to let them run around in 105,000. There is a way on this calculator. Notice, hopefully you can see this. Let me pull this down for one moment. Do you guys agree? If I have this in my calculator right here, this is really the area is equal to this function in terms of its width. Do you agree? Okay, area. Well, why don't we maybe graph something else here? What do you think I'm going to graph? Okay? 105? Yeah, let's do that. So let's delete that. Let's get this calculator out.
That makes, I can figure out now.
Okay? So I'm going to come down, and I believe, let me move this out of the way, it was asking for, right here, 105,000 square feet. So I'm going to go 105,000. Let's graph this out. And I want to draw on this, so I'm going to pull this over. Let's draw on this. Okay. If I go right a certain amount and up, you know what that point means? That point means at a certain width, the area is, so the width, the area is 105,000, isn't it? Because that's how high that line goes up. And this one over here means if I go to the right a certain width and I go up, that is a width, comma, 105,000. Do I have two possibilities here? I absolutely do. And on a calculator from Integrated Math 1, you already know how to find those intersections. What are the buttons? Second trace, second calc, right? And then we're going to find the intersection number 5. And it says first curve, then enter. Second curve, enter. One more time. Here we go. The width would be, in this case, 150. Yeah. So we've got the width would equal 150, and I believe we were working with feet. But is that the only possibility for this area restriction? Not at all. We've got another one, and the other one is going to be right over here. So let's find out what that one is. Second, calculate. Intersect, number 5. And we just need to head over close to the point we're seeking for this intersect to work. All right, so that's close enough. 350. Now, I'm hoping that it makes sense. You can actually imagine what the dog enclosure would look like with that area restriction. All right. So let's shrink this down and come on over. Pull it out a little bit more. There we go. It says, write a quadratic function in standard form that represents each area as a function of the width. Remember to define your variables. Okay, that's a new problem, but I want to make sure that I show you up here these two options. So I could have a width of 150, and this would be 150. What would the entire length be then?
700.
What?
700.
700. You see what I mean? Because combined, 150 and 150 is 300, and we only have 1,000 feet. So 1,000 minus 300 is 700. What's 150 times 700 for my area that these dogs can run around in? 105,000 square feet. But we have another option. The other option was a width of 350. My drawings are absolutely not drawn to scale, but that's okay. If this is 350, this is 350. Help me out. What's this one? 300. And what do you think 300 times 350 is? 105,000. Yes. Yes.